discrete. It's possible to think about it. For people who have studied calculus, then of course that's a different story. But I think that some of the ideas from wavelets are actually easier than traditional Fourier analysis. But they're different, they're quite different. It requires a different way of thinking. But if you first start thinking when you're a second year student or first year student, thinking in terms of this, I don't think it's so difficult. And if you work, you try examples, you work assignments, you use computer models, I really think you can learn it as quickly as you can learn Fourier analysis. And Fourier analysis is not easy either. In the early days of electrical engineering, people thought that engineers could never understand calculus. It was too difficult. Okay, now we teach calculus to freshmen and sophomores, so it's not too difficult.
Hi, Mr. Tavares.
First of all, I have to say that I'm very lucky to sit here and listening to one of the very famous researchers in the ESP, and I have a question to you. As you said that, with as I understand, is localization both in frequency and time. And this morning we have studied that the sometime video transform as Fourier transform. I think it's localization in both frequency and time too. Can you distinguish to transform?
Yeah. It's not easy to explain what you mean by localization, because if I have a signal and I take its transform, the entire signal is in the transform, so there's nothing lost. It's not like there's information lost. So I know both time and frequency. But which parameters are easy to see? And with Fourier, when you take a Fourier transform, you can see the different frequencies. But when things happen, it's not so easy. If you have a seismic signal, so that a signal happens at a point in time, if you look at the Fourier transform, it's very hard to find out where that energy is. There's a relationship that's called the Heisenberg uncertainty principle. And it tells you that if you take a system and localize it in time, the frequency gets wide. And if you localize it in frequency, time gets wide. And if you've ever seen the transform of a square wave, it looks like a sine x over x. And if you make the square wave narrow, the frequency gets wide. You make the square wave wide, the frequency gets narrow. So it's a trade-off. The wavelets do a better trade-off than Fourier. And in fact, in some ways, they're the best that can be done. So there's always a trade-off. And so if you want to have something localized in time or frequency, with the wavelet you can control that trade-off. With Fourier, it's not so easy. It can be done, but it's not so easy.
I have a question. I think in the first part of the just about whether it's so it's difficult to know. But I know it's cutting edge in program. So can you give some application, famous application in the world, so we can have communicate about wavelength application?
Well, both the denoising and the compression characteristics are used. For example, there are some music compression schemes that use wavelet decomposition. So you take music, you decompose it in terms of wavelets, you take a small number of coefficients, record it, same as the MP3, which is a different set of coefficients, and at the other end, when you play it back, it sounds better. But it's not enough better. The trouble with music is that it's not enough better that it's, MP3 is still random. Wavelets is not quite compatible. Nevertheless, wavelets will do a better job It's just only slightly better. The same thing for image compression. For image compression, the wavelets will do a very good job of, if you make a DVD or something, can you compress the signal so it doesn't use so much space? Yes, you can, but some things it is expensive. Denoising. If you're going to denoise medical signals, you take X-rays or something, and you would like to remove noise to see the X-ray picture. Wavelet decompositions can be used there. And there's a variety of electronic communication systems where wavelets are the foundation of them. And the wavelets expand signals in the logarithmic scale. Perfect. So it's going to be wonderful for speech. It's okay. It's good, but it's not wonderful. And part of the reason is that the ear and the wavelet are not that similar. And it's too bad, because if they were, it would be a nice result. But the compression depends on the use. And MP3 works because people hear music and it sounds pretty good. And if the way the music sounds better, well, it's not enough better. So they don't switch and stay with MP3s.
As far as I know about the DSP, all equation we use is linear equation. And in your lecture, you also use the linear decomposition in wavelet theorem. And but in the end of your lecture, you said that in the future we will use non-linear decomposition to for the wavelet theorem. So I want to ask how non-linear decomposition can be used, and what kind of non-linear decomposition can be used?
If I could answer that, I would get still another PhD. So that's a research question. And in nonlinear analysis of any sort, the nonlinearity always has to fit the particular application. Almost never can you have general nonlinear analysis. You can have general linear analysis. But once you start developing nonlinear systems, it almost always has to be attached to a particular application. And I did some work many years ago in nonlinear analysis, and it's just awful. It's just an incredibly difficult problem. Convolution doesn't work. Nothing. All of your superposition doesn't work. Parseval theorem doesn't work. Nothing works. Laplace transform, Fourier transform, all of the tools that we have do not work for nonlinear analysis. So it's a very, very difficult problem. Most of the systems that we build are linear. That's not because linear is best. It's because that's not what we know how to do. If we knew how to do nonlinear, what you're asking is, if I knew how to do that, if I could tell you that, it would be great, but unfortunately I can't. But I would encourage you, you're much younger than me, work on that problem, maybe you will solve it.
I have to know that the wavelet is a very hot topic now. I have a lecturer in seminar in the university in wavelet. We have a main topic in this summer seminars in wavelet, and I have listened to the very interesting talk of you about wavelet. But although is the general wavelet, I want to, if you can show me some research orient, some narrow research orient of wavelet that you think that is very promising in the future.
Wavelets are new enough that many of the applications are not discussed. If a company discovers how to use wavelets to do something, they don't tell other people. That's the way they make money. Is they use that for some competitive